right. Let's go slideshow. Current slide, and we'll go ahead. Okay. First, any questions on anything we've covered up till now? All right. Chapter 2, yes. Oh, no, you don't need the projector. You can read my mind, can't you? Cloudy as it might be, but okay. We've been dealing with matrices. We've introduced them. We're all there. Now, Chapter 2, the title is Matrices. 2.1, Operations with Matrices. Okay? We just did row reduction, that type of thing, but there's a lot of other things you can do with matrices. And that's what we're going to hit on first. Okay? And just try, anytime you run into some new feature, the first thing you do is define what does it mean for two matrices to be equal. And that's the first thing we're going to talk about. In section 1.2, you use matrices to solve systems of linear equations. This introduces some fundamentals of matrix theory and further applications of matrices. It is a standard mathematical convention to represent matrices in one of the three following ways. Okay? Now, you all three have your book? No reason for me to write. Well, do you know if Jonathan has a book? I don't. You don't think so? Okay. Let me write them for him then. Okay? First way you can represent a matrix is by an uppercase letter. And if you'll think about it, this is how we've usually been doing. A, B, C, whatever it happens to be. Okay? Doesn't have to be one of those. I'll put ... The book acts like it has to be one of those three. It doesn't. Okay, number 2. A representative element enclosed by brackets. Okay? Now remember, if we were naming that ABC, one of the matrix, let's just take A, that's everybody's favorite. A, then you would put A equals, open bracket, and then you'd start listing the elements in A, right? So how you represent a, double use of the word, how you name the matrix using a representative element, it would be such as this. I'll write this, a representative, can't spell, element. Okay, and those are enclosed in a bracket. So if you're representing matrix A, you do Aij. Or B would be Bij. C would be lowercase, of course, Cij. And so on. Okay? Now, what's the I and J? They're counters, they're called. Okay, I goes anywhere from, okay, let's size our matrix A. You tell me what size you want it to be.
16.
I can't hear.
16 across.
15 across?
Yeah.
Okay, how many down?
16.
16 down. Okay, that means 16 rows, is that what you mean? And 15 columns, right? He likes them big, okay. 16 rows, okay. Then, if A were that, then I would be any integer between 1 and 16. J would be any integer between 1 and 15. With that, you can pick any element in that 16 by 15 matrix you have there. Pick any ordered pair. That's not really an ordered pair, but any set of integers within 1 to 16 and 1 to 15, and you can locate any one of them and name them that way. So that represents the matrix. Square bracket means matrix, with the representative element Aij, where I goes anywhere from 1 to n, whatever your number there. For you it was 16, and J goes from 1 to m, where m for your case was 15. Okay? Same with B and C. So that's the second way you can name a matrix. The third way is actually the long way, okay? And that would be a rectangular array of numbers, which is exactly okay. And that's exactly what I was describing before. Let's take that matrix A. I'm not going to do others of them, but it would be A11, A12, A13, dot, dot, dot. What would be the last one we would say? A1, if this is a N by M matrix, M, okay? See, oh, they do it the other way. They do an M by N matrix. Why won't they make up their mind? Okay, I'll do it the same way the book does, but I was calling it an M by N. They're calling it an N by M. No, I'm sorry. They're doing, okay. M by N. Okay, sorry, I did it backwards. Okay, N. Okay, and the next, you tell me the next one down. A21, A22, A23, dot, 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 A2N, and we'll do one more, A31, A32, A33, dot, 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 up to A3N, and then we'll do a dot, dot, dot down here, and what would be my last one? M1, AM2, AM3, dot, 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 everywhere dot, dot, okay. What? MN, got it. Okay. Don't you find that a lot easier to just say IJ when I could be anywhere from 1 to M and J could be anywhere from 1 to N? Okay? So much more concise, but you can sure represent a matrix as an array of numbers. That's exactly what it is. Okay? Now, that's how you represent them. Two matrices are equal when their corresponding entries are equal. Okay? So let's go to a clean page here. I wouldn't do this except I'm not sure that Jonathan has a book, so I want him to be able to see all this. Two matrices A, and what would be the shorthand notation for that? IJ, okay, and B. Okay, now, time out. If we're talking about equality of matrices, do we have to use IJ, or, I mean, could that be a different size? And we might need to use KL or something like that. What you think? If they are the same if they're equal, they've got to have the same size. So therefore, you've got to use the same IJ here, okay? In general, when you're talking about two matrices that not talking about equality, they could be different, okay? So then you would need different subscripts. But if you have these two matrices, this is indicating they have the same size, okay? These are said to be equal when they have the same size. That's what we just said. When they have same size, M by N, and that's why we can use I and J, because I is going from 1 to M and J is going from 1 to N, okay? And also, the other thing is Aij is equal to Bij for every I and J out there. And the I is going from 1 to M, and J is going from 1 to N. Okay? For all I's between 1 and M and J's between 1 and N, every one of those entries has to be the same. Okay? So let's look at example 1, pretty simple. Let's see, do I need a clean page? Let's do it, just in case we need more room. Okay, here's matrix A. A real creative 1, 2, 3, 4. What an original sounding matrix. Okay, and here's B. 1, 3. Is that a legitimate matrix? Sure. If your N is 1, then J would be going from 1 to 1, which is only 1. Okay. How about this one? C equal 1. Ooh, I always want to put, not always, but quite often get the writing too fast and put commas. In matrices, you don't put commas. 1 and 3. Is that legal? Sure, in this case, your M is 1. That's the only value it'll have, so that's perfectly fine. That's a legitimate matrix. And here is D. A 1, 2, X4. All right. Now, are matrix A and B equal or not? No. What's the first thing that slaps you on that one? They're not the same size. Two matrices cannot be equal unless they're identically the same size. A is a what? A is a 2 by 2. And what's B? Second? I know, but what size would you call it then? M by N. Huh? M stands for rows. Those are 2 rows. They just got 1 element in each row, not very long rows. So that's a 2 by 1. What would C be? 1 by 2. How about D? Two by 2. So A can't be equal to B. A can't be equal to C. Could it be equal to D? Under what condition? Say again? Yes, under the condition that X equal 3. If X is equal to 3, you think of X as being a variable. Now, if X was just a letter, a symbol, then no, they're not equal because the symbol 3 is not the same as the symbol X. But if X is a variable, then they would be equal if and only if X was equal to 3. Because all the rest would be the same, you would have to require X equal 3. Okay? Then they would be. How about B and C? Same numbers, but not the same size. You're absolutely right. Cannot be equal unless they are identically the same size, M by M. Okay? Good deal. Now, that leads to another thing that they mention here, and we don't use it again for chapters, okay? Well, for quite a while anyway. That you can partition, okay, let's time out again. A is obviously a matrix. And B was giving Nigel some problems here because it doesn't look like most matrices. It only has 1 column. So therefore, we call that sometimes a special name, a column matrix, because it only has 1 column. And later, we'll actually give another name to it. It can also be called a column vector. Any matrix with 1 row or 1 column can also be named as a vector. What do you think 2 other names for C might be? Row matrix, all right? Row vector, exactly. Okay. So those are matrices, but if they only have 1 column and 1 row, then they could be called either a column matrix, a row, sorry. Sorry. I can't talk. A column matrix or a column vector or a row matrix or a row vector, like B and C there. Okay. But that's not all. Let's just imagine you partitioned A the same A we had before, 1, 2, 3, 4, into 2 column vectors. In other words, and what they did, and here we have Jonathan. We have perfect attendance. Way to go, team. All right. I want to run this by you in case you're interested. Do you have a book?
No.
No. This is not the same book, but it covers the same material in a little bit different order, but it has everything in this one is in that one. I mean, not maybe every section or something, but the concepts are there. I got in the mail last week, I guess it was probably around Tuesday or so, may have even been Monday after class, the second edition of this. They've come out with a new edition. This one has been on my shelf for a while. And so I don't need this anymore. They have a second edition. So I was going to toss it. But before I tossed it, I wanted to see if any of you wanted it. It's not the same book, but it has the same material. Are you interested in having it? Sure. Okay. And of course, it won't be the same exercises and stuff like that, but it should be the same concept. Okay.
Thank you.
Glad to. I had it Wednesday, but I started teaching before anyone came in. Then when y'all started coming in sort of one by one, I forgot to go back and say anything about it. And when I was later leaving, I said, who left it? Ooh, that's my book. Okay. Now what we're going to do here is draw I'm going to use the same color they did, imaginary line between those two columns in A. And what we've said now, we've partitioned matrix A, and that's the name for it, into 2 columns, okay? And that would be A1 and A2, where A1 is a column vector and A2 is a column vector, but I need to put my partition symbol in there as well, okay? I skipped a step, didn't I? No. Yeah, I did. No, it's fine. I did. I just drew the line through the other. Okay. Now, they don't say it, but guess what? You could also take that matrix A, or any old matrix that has more than one row or column, and do the same thing, if I could write, to the rows. Okay? You could partition this into two row vectors. Okay? Now they don't show this, but you could, and there's nothing wrong with it, and that would be, let's give it some other things. Let's call it A3, A4, because I don't want you to think those are the same. Not doing things well here. Okay, it would be a partition, and you had row vector A1, 2 on top, that would be A3, and row vector 3, 4 on the bottom, that would be row vector A4. Okay. You can name those anything you wanted to, I just named them similar to what the book did. So that's partitioning a matrix. Of course, to partition it, you really need more than one row and more than one column for it to make a lot of sense. All right, that done, let's talk about adding 2 matrices. I don't even know what chapter this is for yours. It's probably not far from chapter 2. It may be, is it in that book? Okay.
Well, I mean, what's the section called?
The chapter is called Matrices, and the section is Operations with Matrices. Isn't there a chapter with something similar to that? Okay, here's matrices, and probably matrix algebra. Now, if you find it's way, way different, let me know, because I'm thinking about changing from this book to that book. Not that I dislike this book. It's a pretty good book. I really like the author, especially in his other books. But in this book, he still does one thing that most authors don't. CalcChat.com, worked out solutions for odd number exercises. That one I don't think has anything like it. But what that one has, this one doesn't, are PowerPoints, or at least they claim they do. So I'm interested in seeing. Now, I've used that publisher before in my calculus course, and you know how lousy the PowerPoint is there. I'm hoping they're better than that. If they turn out just being that, I may give a second thought, you know, but still, it would be so much better to have the PowerPoints than have to write everything out. So, anyway. So now we're going to talk about, and this is when that's why I say algebra of matrices, this next thing should fall right under there. Okay? The definition of matrix addition. Okay? So let me clear the screen here. If A, and they're giving the two different ways to express it, A is equal to, how would you express that in, what do you call it, component notation? What would that be? Little a, ij, okay? And B, now again, if we're talking about adding these matrices, do they need to be the same size? Yes, they do. So you use the same counters, B, I, and J for B. They are matrices of the same size, M by N, okay? If that's the case, then the sum is also an M by N matrix, same size, given by A plus B, and how you represent that, which I hope you would guess, would be Aij plus Bij. Now notice that's still a single element. Wherever that is in your matrix, it's one element that takes the Aij here, adds to the Aij, the Bij here, and that's how you get the new element. That is a single operation, single element. There. And notice you have to add the corresponding ones. The sum of two matrices of different sizes undefined. Let me write it another way. Cannot add two matrices of different sizes. Just can't happen, because you're going to have either some row or some column left over with nothing to add to. So it wouldn't make any sense. They have to be identically the same size. Okay? Any questions on that? Let's look at example 2. This is all pretty easy stuff. So let's do A. -1, 2, 0, 1. Is that a legitimate matrix? What size? Okay, what size was that first matrix? 2 by 2. How about the second one? So you can't add them. What would be the resulting matrix? Now, you can do it several steps the way the book does, or you can just add them element by element. And what would that be? 0, 5, -1, 3. That's it. And guess what? It's the same size as the first two. Has to be. You have to have the same size. Okay? All right, let's try another one. This is B, 0, 1, -2, 1, 2, 3. And you're adding to that. And what size is that first one? 2 by 3, excellent. Adding to that, this really creative matrix here, 0, 0, 0, 0, 0, 0. Can you add those? What size is the second one? 2 by 3. Can you add them? Okay, do so. You might need your calculators, okay? 0, 1, negative 2, 1. Without a calculator even, I'm impressed. Okay, good deal. Now, this is a rather silly looking matrix, isn't it? You know what we call it? It has a name. No. Simpler than that. The zero matrix, okay? So you could call that the zero matrix, but any matrix with all the elements being zero is by definition a zero matrix, but you have to identify which zero matrix you're talking about. So this would be, it's called the zero matrix. That's supposed to be a capital zero there, a bold zero. But you have to specify this is a 2 by 3 zero matrix, meaning all the elements are 0, okay? And this will say if this is matrix A plus the zero matrix of the same size, so A may be a 2 by 3, okay, then this is always going to be what? A, 2 by 3, okay? We call the zero matrix, if it's the right size, the additive identity element, meaning that anything you add to it comes out identically the same as it was going in, okay? Just like we did this number 0 in addition. 7 plus 0 is 7. Negative pi thirds plus 0 is negative pi thirds. It doesn't change it at all, okay? Now, let's go to the C one. Any questions on these? All pretty straightforward. How about this one? Here's a 1, negative 3, negative 2, plus negative 1, 3, 2. Okay. Give me 2 names for that first one. What's that? It's a 1 by 3 matrix. No, it's not. 3 by 1. 3 rows, 1 column. Okay? All right. Give me another name that you could use for it. What? You could name it A. Yeah, you could name it anything you wanted to. But what, fishing here. I can't think what bait to put on my hook here. What type of a matrix could you name that? A column matrix, and another name for that would be a column vector, and added to another column matrix or column vector of the same size. Both of these are 3 by 1s. So add them and see what you get. Zero, 0, 0. All right. That is called the 0, 3 by 1 matrix. Okay? Now, these two, any two matrices that add to be a 0 matrix, of course, same size they have to be the same size. That would the, or vectors, column vectors, or column matrices, however you want to call it. So this could have been done if this was a 4 by 7 matrix, as long as every element in the second one was exactly the opposite of the element in the first one. That would add to the 0 matrix then these would be additive inverses of each other. We usually don't refer that way because when we say an inverse of a matrix, we mean something else, and just to keep from confusing, we usually don't. But anyway, let's go on and look at D. Here is 2, 1, 0, 4, 0, 1, negative 1. I'm going to add to that 0, 1, negative 1, 3. And what does that give us? Absolutely nothing. Not 0, nothing. It means it's undefined. You cannot add matrices of different size. What size is this one? Say again? 2 by 3, and this is a 2 by 2. You cannot add those. Cannot at all. Okay? Not defined. Okay. Or is undefined. Doesn't matter which. Now, when you're working with matrices, real numbers are referred to as scalars. Okay? So each of those elements in there is a scalar. Yeah, that's fine. We've been using all integers so far. You don't have to, okay? But to multiply a matrix by a scalar, matrix A by a scalar C, we simply multiply every element by that. Let's just pick one of these. Which one you want? One of those column matrices or column vectors, or one of the last two down here? Pick one. Anyone, I don't care. Which one? Which? First or second? Second one? Okay. I'm going to erase everything else then. Okay. I'm just, so I don't have to write as much. Sometimes a little easier to erase than it is to write. Sometimes not. But in this case, I think it is. Okay, I want you to give me a number. Any number. Say again? 2. Okay. What if we multiply the scalar 2 by the matrix A? What do you think that would be? 0, 2, -2, 6. Exactly what you might imagine it would be. That's called scalar multiplication. Multiplying a matrix by a scalar. Now, you can also go the other way. If you started with this matrix and looked at that and said, hey, all those numbers are divisible by 2, then you could factor out the 2, but you have to factor it for every element, every row, every column, right? So you can do that. And they give you another example where that would be a very convenient thing to do. Nigel would love this matrix. But maybe the rest of us wouldn't love it quite as much as he would. What could you do to that one? Say again? Are there any common factors? 1/2. Factor out of 1/2, and what have you got left in the first one? 1. -3. 5. 1. Sure enough, there you have you've gone the opposite direction of this one. You actually factored out a common factor. Okay? So this equality goes both ways. If you're multiplying by a common factor, multiply every element by it. Or if you're dividing one out, do that. Okay? Okay. Now, so here is the formal definition of scalar multiplication. I think you already know how to do it. Let's just write it somewhat formally. What's another name for A? Aij, where J goes anywhere from, I goes anywhere from 1 to M, and J goes anywhere from 1 to M. So that's an M by N matrix. Okay? And C is a scalar. Okay? Then, the scalar multiple of A is defined by the number C, okay, is also an M by N matrix. Multiplying by a scalar does not change the size of a matrix, and it would be given by CA, and how would you express this? CAIJ. Every element in A, every AIJ, for I from 1 to M and J from 1 to N, every one of those gets multiplied by that scalar C. Okay. Most of the time, scalars are given lowercase letters, and matrices are uppercase letters, so you'll know which is which. Okay. Now, what would we mean by this symbology, negative A? What would you think that represented? Say again? You got it. That would be the number -1, the scalar -1 times the matrix A. What would that do to every element in matrix A then? Multiply -1 by every AIJ. Okay? In other words, it changes the signs of every element in the matrix. Okay? Now, what if A and B are the same size? And they don't say it, but let's just assume they're M by N's. Okay? Now, what would you think this represented? A minus B. There's two ways to look at this. What would you interpret that to mean? Say again? And what would that mean to you? Say again? It would be just like subtraction. So what I hear you saying is, and you tell me if this is what you meant. For every element in A, Aij, you would subtract then Bij. And carrying that out a little further, that would make a new matrix, which would be every element Aij would be Bij subtracted from it. So there's your new matrix. Okay. That is certainly one way to do it. That's how I usually do it. But another way you could look at this would be A plus -1 times B. Right? Because didn't you just tell me that minus A represented -1 times A? So that would be this. So that would be Aij plus a -1 times Bij, which would be exactly the same thing that we have here. So there's lots of ways you can get there, but that's exactly what you would be doing. So let's do example 3, which is a little more involved than the others we've been doing. Others have been pretty straightforward. Now we're going to do multiple operations. We start with defining what A is. A is this matrix here, 1, 2, 4, -3, 0, -1, and 2, 1, 2. Used to be a defense we ran in basketball, okay? So, okay? And here's your B, and that's a 2, 0, 0, a 1, -4, 3, and a -1, 3, 2. Okay, there's your two matrices. Now, the A problem says find 3A. Can you do that right off the top, or do you need extra room writing it? Do it, and what would that be? 3, 6, 12, -9, 0, negative 3, 6, 2, no, 6, 3, pretty tall, okay. Let me get that cleaned up a little bit. 6, okay. All right, good. Got the A part done pretty well. What would be the B part, negative B? What would that be? Negative 2, 0, 0, negative 1, 4, negative 3, 1, negative 3, negative 2. Very good. The C part says what is 3A minus B? What you reckon that would be? Second? Okay, so what you're doing is adding this one to that one, which is exactly correct. So that would be a 1, 6, 12, negative 10, 4, a little louder, negative 6, 7, 0, and, oh yeah, right, 4, okay, sorry. I was looking at the wrong one. 4, very good. And I think that's what the book got too. Excellent. Way to go. Make sense? All right. Now, do you have to do them in that steps? No, I mean, you could do them any way that, as long as you're doing it correctly, you could do it. I mean, you could have started over and done element by element. And however you see and understand best, go for it. Okay.
So on that, could you have done A minus B and then multiply by 3?
No. No, you could not. Okay. What you just described was 3 times A minus B. And that would be 3A minus 3B. Okay. So, yeah, that's different from what they had here. Yeah, good question. Excellent question. So, guess what? Up to now, we've added and subtracted matrices. Can we multiply matrices? Yes, but probably not the way you would think. Okay? Warning, warning, don't just go crazy on this. To see the usefulness of this operation, we'll start with an example, an application, not just giving you a rule. Okay? Here's the application. We are at a football stadium. They only have 3 stands. South stand, north stand, and west stand. Evidently it faces east, and that's where the entrance is or something. There's no stand there. Okay? So we have south, north, and west stands. Okay. At each of these stands, you have a vending area. The vending area sells 3 products: peanuts, hot dogs, and sodas. This must have come from the north somewhere, don't you think? Down here we call them Cokes. No, I mean we call them, no, actually sodas wouldn't be too bad. Pop, that would definitely be from some other part of the nation. We don't call them pops much, do we? Not that I've ever heard. Okay? And let's say in the north stand, south stand, you sold 120 bags of peanuts, 250 hot dogs, and 305 sodas. Okay? This is a reasonable problem. In the north stands, they were pretty hungry there. 207 bags of peanuts, but only 140 hot dogs, but 419 sodas. Of course, you see, the north stands would have the southern sun on them, so they got hotter there. I don't know. I'm just making that up. In the west stands, this is in the end zone, and not as many people want to sit there. So they only sold 29 bags of peanuts, 120 hot dogs, and 190 sodas. Okay. That's all well and good. That describes everything in a simple matrix. Your whole vending operations at the stadium during that game. Except we don't know what they sold them for. Okay? And that's what the next matrix would be. And this is a column matrix or a column vector, would be the selling price. Okay? The selling price was $2 for your peanuts, $3 for the hot dogs, and $2.75, I love that, for your sodas. Okay? Now, could you tell me from this information how much revenue you got either from each set of stands or each vending area or from the whole thing? Let's start with something simpler. Pick a stance. Take a stand, folks. Okay. Either south, north, or west. Take one. South, okay? Okay. From the south stands, how much revenue did you get? How would you do that? Multiply 120 by $2, right? So that would be $240 is how much you got from selling the peanuts. How about the hot dogs? What would that be? $7.50. And from selling the sodas. I love this, but I'm going to need a calculator on that one. 305 times 2.75. Come on, somebody. Huh? 610 on the nose? Oh, you're just guessing. I think that might be a little low. Believe so, because if it's $3 each, that'd be 900 and some. And say again? That sounds a little bit better. I thought it had a decimal in it. Okay. So say it again. 38.75. So how much revenue do they get in the stand? I can do the first part, 0.75. I got that one. Okay. And the 8, I can even do that one. Okay. And then we got a 10. No. We got 8 and 4 is 12. Carry a 1. Be 3, 10, 18. Is that right? Doing it in my head. So that's how much moolah they brought in there. I mean, that would be revenue, not profit necessarily, but revenue. Okay? And then you could do that for all the stands. And then you can add them all up. Okay? So yeah, you can come up with everything that you needed there. Now, notice how we did that. Because it sort of made sense. Well, notice first, what does each row represent? But it's sold from a certain concession area. The south, the north, and the west concession areas, right? The column stood for products. Over here we had rows standing for products and the column for the selling price. So what we get here, when we're multiplying these, you multiply row 1 by column 1, okay? Because this is referring to the product, but these, okay, this is the stand, this is the product, that's the product. So basically, the column and the rows here have to be the same. If you had another column here for chips, but didn't have things here, you couldn't even do it, could you? Okay? Or if you had a fourth area here for chips, but didn't have chips up here, you couldn't do it. So here is what you're having to do. Multiply like this, and then if you also are doing the north stand, you do like this, and then the west stand like this. That's how you do matrix multiplication. So it's very different from addition and subtraction of matrices. What's the first big difference you see? They're not the same size, okay? Now they could be. They could be the same size, but in general not. They don't have to be. Addition, subtraction, they have to be the same size or you can't do it. But here's what you do have to have. The number of columns of your first matrix must equal the number of rows of the second matrix. Has to be. And then, here's the other part here. If you did the north and the west too, you would have some number here and some number here. That would be your result, right, when you did those multiplications. Well, this is what size is that first matrix? 3 by 3, and this one was a 3 by 1. And when you multiply them together, the number of columns here had to equal number of rows there. So basically, this is not quite fair. Ignore them. I won't say cancel them out, but you really aren't. Just ignore that, and your answer matrix is a 3 by 1, the solution matrix. And that's going to be the same every time, okay? So, yeah, the 1828.75, they did the math and came up with 1986.25 for the north stands and, 940.550 for your west stands, okay? And that's how you did the multiplication. So let's move on to a definition for that, okay? If A is a matrix Aij, okay, and M by N matrix, okay, and B, now notice here, the little b here, they have, okay, they're using the same subscript. Don't let that fool you, okay? Here's where the important thing is. B is a N by P matrix, okay? Now, I really don't like using the same subscripts if they stand for different numbers, okay? It's fine in addition, subtraction, because they are standing for the same numbers, okay? But I would have said B would be JK or something like that, because I here is going from 1 to M, J is going from 1 to N. Over here, your I is going from 1 to N, and the J is going from 1 to P. So since they have different values here, I would tend to write that as JK. To emphasize that the J here and the J here have to have the same range of elements. And the I and the K's are very different. They say it with the second part, which is, that's the important part. They've got to be different sized, or not necessarily different sizes. They have to have the number of columns for the first matrix has to equal the number of rows for the second. Doesn't matter what the number of rows for the first or the number of columns for the second is, but you have to have the number of columns of the first equaling the number of rows of the second. Okay, so there's your matrices. Then the product, okay, AB, and that's how we usually write it, is an element Cij. And again, I think it would be clearer if they had used different subscripts, but it's fine. Where Cij is, this is written in math speak, the summation from I equal 1, no, K, I'm sorry, thought you can't do that, okay, and you can't, okay. You could do it a little bit differently, but K is equal to 1 to N, okay. Now remember, your N is the number of columns in the first, rows in the second, okay? So you're going to have a summation, just like we did before, K going from 1 to N of A I K times B K J, okay? That is going to define. So in other words, the number of rows in your product matrix, Cij, number of rows is going to be the same as the rows in A, and number of columns is going to be the same as the columns in B. Okay? Because you're multiplying through and sort of, in a sense, ignoring the columns here, rows there, because they have to be the same. And when you add them together, you wind up with just Ij. You don't have a K anymore. And that's why I wish they had changed their subscript numbers, letters, just to make it clear. Okay? But this is fine. This is absolutely correct. Well, what does that mean? That would be then A I1 B1I 1J plus A I2 B2J plus ... until you get to A I N times B N J. Okay? You're doing 1 to N. Okay? And when you add all those together, that's the new element, Cij. And then you do it for every one of them. Then you let I go to 2 and J go to 1, or whatever. And you do every element like this, adding those up. Now, to me, this is kind of blah, blah, blah. Okay? When you actually do it, I think it makes, hopefully, it will make a little more sense. Okay? The sad news is, I don't think we're going to have time to do example 4. I wish we did, but we're almost through with time. So we'll start next time with example 4. Okay? On page 43. But the good news is we got enough covered to do some homework. Okay, and by the way, those who came in a little later, I did not get the test completely made out for chapter 1. And as I was telling the others who came here first, I'm going to have incredibly little office hours this week. I mean, same number of office hours, but so much to do in those. For instance, today's office hours from 3:15 to 5:15 basically are going to be spent almost entirely. The thing my boss came up with, all department chairs have to have a syllabus from every course, from every instructor offered in fall and spring of last year. And that is going to take an awful lot of work to get those together. They're due tomorrow. And between now and then, the only office hours I have are 3:15 to 5:15 today and 11:15 to 12:30 tomorrow. And that's all, folks. And that's in addition to everything else going on. So I hope maybe to have your test done by Wednesday, but I can't swear to it. Okay, so here's your homework exercises. Any of the, either 1 or 3 or both, those are really, really easy. I would do them both. And then any of the odds, 5 through 11, which is in operations with matrices. Okay? Then I think you can do 13 and or 15. I'll let you choose those. But stop there because we haven't done products yet. So either 1 or 3, any of the odds 5 through 11, and then either 13 or 15 or both. All right, good deal. Any questions? All right, we will see you then on Wednesday. Well, I see all of you later today in some other class, right? And it varies. Let's see. I'll see Jonathan and Nigel in differential equations last thing today. And I'll see the other 2 of you, Emmanuel and Marcus, in right after lunch.
Did you get that test now?
What's that?
So you got the test for linear differential equations now?
No. You see, if I thought I had to have summer schedule done Friday, so I was working on that, and then when my boss came in, he said, "Oh no, I don't think we need those till next Friday." I went, If I hadn't taken my books over there, I would have done those first, but I didn't have them there. I was on Birmingham campus, so I'll try to get
So
those.
like different examples, but can I still keep it?
Huh?
I said look at different examples, but can I still keep it?
Oh, absolutely. That's what I said. If it's beneficial to you, take it. Even if you're getting a book later, if it's beneficial, you can keep it. If not, give it back, and I'll give it to somebody else if they want it. But none of the other 3 in here wanted it. So, all right, glad to. And I recorded all that. Sorry.